Hello, everyone. Welcome to the third episode of the video series for the AI data centers. In the last episode with Himanshu and Mahesh, we discussed how load balancing is enabled in the AI data center fabric with features such as dynamic load balancing and global load balancing, improving the efficiency of the fabric. To kick off our discussion today, I'm joined by my special guests and good friends, Mahesh Subramaniam and Michal Styszynski. Today, we will discuss the cutting edge congestion management technologies needed for the lossless Rocky V2 transport networks when connecting the GPU clusters. Mahesh and Michal, welcome to episode 3.
Hey Arun, hey Mahesh. Hey Arun, great to see you again.
Hi, Arun. Happy to be in your video again.
And looks like today I did not get the memo.
Yeah.
So let's start with you, Mahesh. In the previous video, we discussed the advanced load balancing techniques in the AI data center clusters. Also, these backend AI clusters are often 1:1 oversubscribed or have very efficient load balancing in place. So, why is congestion management still needed in the AI clusters?
Yeah, Arun, congestion management, even it starts from the efficient and effective load balancing. Everybody knows that in a cluster infrastructure, the overall goal is to have a reduced job completion time. That's a key KPI. But in a data center infrastructure, our key KPI is a lossless fabric. Because during the RDMA transition from one GPU to other GPU, even a single drop will make the job cycle to run again. So the real game here is to how we are handling the congestion proactively versus reactively. What I mean here is that in a GPU cluster on the fabric, we have to control the congestion proactively using efficient load balancing. Little bit in detail, in the proactive method, we'll make sure if any congestion happen on the particular link or a path, we will switch that particular flow from congested link to less congested link, right? During various method, last video also we discussed like a DLB, dynamic load balancing, or selective DLB, identify the BTH header, elephant flows, and accordingly it will spray the packet. Various methods are there. But at any point of time, due to microburst, if any link got congested, we have to immediately jump in, do some reactive methods. That's where we have a proper congestion method coming into the picture via ECN and PFC as of today.
This is an interesting start, Mahesh. Can you share a few scenarios in the reactive approach?
Yeah, there are multiple scenarios are there, but I want to go a little bit of basics. In any data center, we have a different congestion points, and we have a called as in-cast congestion points, right? What is in-cast means basically multiple input to only one output, it will make a congestion. This particular in-cast congestion generally it will happen in 3 points, where a GPU cluster to leaf, that's a point 1, or leaf to the spine, which is point 2, or spine to the leaf, this is point 3. So how we are going to handle the congestion in the switch or switch fabric, that's where we need a proper congestion methods. And since you asked about the scenarios, like for example, we have a kind of a in every A6, in every switch in our A6 have a MMU, which is memory management unit. This memory management unit has two parts. One is that ITM, that ingress traffic manager, and ingress traffic manager 0 and ingress traffic manager 1. This ingress traffic manager ITM will allocate the buffer to our switch. It can be a dedicated buffer or it can be a shared buffer, depends upon the ASIC and switch what you are using it, right? In the queue, in the buffer, it got filled, then became a congestion. So we need to avoid the congestion. That's where we started using some kind of a key congestion mechanism for a Rocky V2 traffic. And we can call it as a DCQCM, the data center quantized congestion method. In the DCQCM is nothing but the combination of ECN plus PFC. That's what we are going to see it is in the video in detailed way.
This is very helpful, and I want to move to Michael here. So, Michael, can you remind us what are the main building blocks of the condition management?
Yes, Arun. So in fact, there are two methods, right, for congestion management, right? The explicit congestion notification is in fact the most popular portion of the congestion management. And there is obviously the second mechanism, which is the priority flow control using the DSCP. Both of these mechanisms run on the native IP fabrics where you have leaf spine, super spine topology. But in some scenarios, only the ECN, the explicit congestion notification, is used as a primary one, which simply informs the destination server about the congestion, right? So, of course, there is a prerequisite to put this functionality on the switches. And without having that functionality on the NIC cards, we can't really rely on that congestion management. So that's the portion which is very important, making sure that the congestion management we are triggering on the switches is also supported on the NIC card itself, right? So the driver of the server has to be capable of interpretation of the ECN messages received from the network, right? And so the ECN is simply a mechanism which will inform the destination server about the congestion when actually it reaches the threshold set at the per queue level on the switches, right? So, for example, you set in your spine devices on a specific queue, on the lossless queue, that when you reach that threshold, you will start marking your packet with 1 beat, which is the most significant bits of the TOS on the IP, and you will inform the destination server about the scenario of the congestion, right? In this case, the server will get that information and will react to it, right? So it will send back the information to the originating server, and it will just mark it with specific values to inform it that he needs to slow down a little bit for a very short time, and then reduce the congestion or simply eliminate the congestion, right? So when it sends back the CNP message to the originating server, the source of the Rocky V2 packet, then it will get this information with the dest queuper information so that we know exactly for which session it needs to reduce the rate. And also the partition key is part of the information, right? When it sends the CNP packet back to the originator, right? So then the partition information, the logical information is also leveraged so that the originating server knows exactly on which of the session it needs to reduce the rate in order to prevent from having this congestion inside the network, right? And then the second mechanism, PFC, is actually triggered just after the explicit congestion notification when actually the congestion still happens, right? So if we trigger the ECN and ECN actually reduce the congestion, then the PFC sometimes it's not even triggered, right? Back to the originating server, right? So instead of having a situation of a switch which sends both PFC and ECN to the destination, PFC actually is sent to the originating server directly from the switch. Hop by hop, it's acting on each of the segments and can inform also additionally on each of these segments to slow down, reduce the rate, and then again, prevent from a scenario of congestion inside the network, right? Both of these mechanisms are supported on the switching side, but again, I will repeat that it's also important that we have a right interpretation of these values on the NIC card. The good thing is that both of these mechanisms are the most widely supported congestion mechanisms in the industry. There are other ideas about how to run the congestion management on the fabric, but the reality is that you need both of these portions. So this one is really the most popular one and is available across multiple vendors. So you can build your Rocky V2 AI ML fabric using different vendors, and they can support both of these standardized mechanisms for the congestion management, right?
I'm glad you mentioned that they are very well-known and methods, both ECN and PFC. So are there any nuances in these techniques for the AI data centers?
That's a good point. So, Arun, last time we discussed about some more advanced functionalities of how to, for example, manage the PFC using the concept of alpha values, right? So you can set different values of alpha, and then provision the way the X off is actually triggered to actually pause the streams to the originating server, right? So these values can be actually enabled at the per queue level, and then you can, for example, decide that for very specific large language model, you will actually provision a little bit more of the buffer, so the trigger of the X of the PFC messages will happen with lower probability, right? So that's one thing. The other thing that we discussed last time was also the PFC watchdog, quite popular functionality across different vendors, where if you rely on PFC, if it's the case of your network, you can actually control the situations where the network is experiencing some abnormal triggers of the PFC, where the rate of the PFC is received too often. Then on the switch, you can say, okay, if I get too much of these PFC back pressures in the given window of time, I will simply ignore them and just stop pushing it down to the originating servers, right? But you asked me about some nuances, right? There are other nuances. So one of the nuances is simply at the switch level, how you handle your buffers, right? So the way you can handle it is, of course, do it at the per queue level for specific congestion management mechanism, as we said, using the alpha values for the PFCs. But also on the switch itself, you can manage these buffers and reallocate dedicated buffers from the interfaces you are not using, for example, on your switch, reallocate the buffer memory to the shared pool, and then give a little bit of more of the buffers for the shared pool in order to be used in case of the congestion situation, right? So that would be another area to explore whenever you have a leaf-spine, super-spine IP fabric topology, making sure that you have a consistency at each of the level in terms of the treatment of your buffers, right? So very important buffers associated with the congestion management that we discussed so far, making sure that the switch is provisioned in the right way.
Great points, Michal. I think this has been a great session so far. But before we close, I must ask this question, and I'll go to Mahesh here. Mahesh, what other technologies are being enhanced to support the AI data centers?
Arun, you asked about a data center. In the fabric perspective, there are two things you know that. One is that congestion management and load balancing. In a congestion management, in both areas, there are a lot of things happening. Let me start with the congestion management. Of course, there are how we are going to handle this congestion and queuing mechanism at the edge. We'll call it as a EQDS, HQ datagram services. And also, of course, you guys know Amazon already started using a scalable, reliable datagram and in the transport level. Plus, in the Ultra Ethernet Consortium, we are very well part of it. There is a fast CNP, we'll call it as a source flow control, I think 8.2.1 QDW, the standard which is evolving. Drop congestion notification, congestion signaling, how we are going to handle the congestion tag and how you're going to reflect, that we'll call it as a congestion tag and congestion reflection tags. How we are going to handle it, these are things are happening in the congestion management area. And forgot to say one more thing, there is a credit-based flow scheduling or control. That is also one of the key thing. It's happening in the Ultra Ethernet Consortium. We already, myself, Michal, and one of my colleagues also started doing a lot of research on it. And soon it will be, once it's available, definitely it will be incorporated in our switch as well. That's for congestion management. For load balancing side, there are many things happening again. One of the key feature under the cognitive routing, Broadcom introducing a GLB, that is a global load balancing mechanism. The dynamic load balancing is a local significance where the GLB can communicate the quality table and the link queue depths from one switch to another switch using their proprietary EAP mechanism. That already we started supporting in our Juniper switch portfolios. And the second is that in-network collectives. That's going to be soon, it's going to be the talk of the town. And basically what we are going to do, how the collectives going to communicate from one fabric to another fabric via one switch, one server to another server via fabric. That's nothing but in-network collectives. How we are going to reduce the data copies and how we are going to reduce the data movement in the consequence we are going to reduce the link utilization, and automatically job completion time will be reduced. These are the two things we are working on. And of course, the thermal management, power efficiency, the key things, even in our strategy also, we are incorporating, which we will be doing a deep dive in further videos as well.
It's been a great learning experience, and I'm sure viewers are enjoying as well. Listen to both of you. So, with that, we conclude our today's session. Thank you both, and to our viewers, stay tuned to learn more, and we'll be coming up with a new episode shortly.